In part 1 of this video about interference, we have studied about the phenomena of interference, as well as we came to know that we get redistribution of energy on the observation screen when interference happen, and because of that redistribution we obtain bright and dark alternate bands, and we call that bands as interference fringes, and these are bright fringe and dark fringe. Now in this part we are starting with the expression of the fringe width of these fringes. So the interference fringes we are obtaining, we are going to find their width, that is interference fringe width we want to calculate. So again for that we are going to consider the setup of Young's double slit experiment. So in the setup we have a source placed such that it illuminates a narrow slit S. So this slit S is illuminated by a monochromatic light source of wavelength lambda. So we are assuming that source has wavelength lambda. Then after that there are two narrow slits S1 and S2 arranged symmetrically with respect to the slit S. Now since these are derived from the same parent source, the light that are coming from S1 and S2 is coming from the same parent source, so these two S1 and S2 slit, these two behave as coherent sources. Okay, so these two behave as coherent sources. That means the rays that are coming from S1 and S2 can superpose and give us the results of interference. Now these slits, these two slits S1 and S2, which act as coherent sources, these are separated by a distance small d. That means if this is the center of the setup, then the distance is this distance, let it be a. So AO is d by 2, and similarly here if it is b, then OB is again d by 2, right? And AB is the distance between the two slits S1 and S2, which is a small d, and the screen is placed away from this slit by a distance capital D. The path difference between the two interfering waves here is equal to the difference between S2P and S1P. So the path difference that we need, let us denote it by small p. So this path difference P is equal to S2P minus S1P. So now our task is to find this path difference. This we are going to do by using this diagram. So first of all, from right angle triangle S2BP and S1AP. So we are using these right angle triangles, and from triangle S2BP and triangle S1AP, what we have, S2P square minus S1P square is equal to, we are applying A square minus B square identity here, and along with that we are also applying the values of S2P and S1P by using Pythagoras theorem. So S2P square minus S1P square, the left hand side can be written as S2P plus S1P into S2P minus S1P. This is left hand side. Now for right hand side, the value of S2P square is can be found by this triangle. So S2P square will be equal to S2B square plus PB square. So this is equal to S2B square plus PB square. This is the first value, minus for S1P square we have the value S1A square plus PA square. So here we have used Pythagoras theorem, S1A square plus PA square. Now substituting these values we get S2B and PB. So S2B is D and PB is x plus D by 2. So this is D square plus x plus D by 2 square, the first bracket, minus second bracket is S1A is again D. So this is D square plus x minus d by 2 ka whole square. Now if we solve right hand side, d square and d square will cancel out, and by solving the whole equation we get the value s2p plus s1p into s2p minus s1p is equal to 2xd. On rearranging we get the value of s2p minus s1p, which is the part difference, is equal to 2xd upon s2p plus s1p. Now this quantity is unknown, s2p plus s1p. Now we have to substitute this. So practically the point p that we have considered lie very close to O. The distance x is very small, this p is very close to O. So in that case the distances s1p and s2p are approximately equal to the distance between these slits and the screen, that means capital D. So since practically point P lie close to O, that means x is very small, so in that case s1p and s2p both are approximately equal and are equal to D. So these values are approximately equal to D. So in both places for s2p and s1p we are substituting D, so it will be D plus D, that means 2D. So the part difference P will be s2p minus s1p is equal to 2xd upon D plus D, that is 2D, or it is equal to xd upon capital D, where small d is the distance between the slits and capital D is the distance between slit and the screen on which we are observing fringes. Now this is the path difference. Now what is the position of bright fringe? So there are two possible situations, one is for constructive, other one is for destructive. So again we are splitting it into section. For constructive, first we are talking about constructive. So constructive के लिए we know the condition that path difference should be integral multiple of lambda. For constructive interference, the path difference P, that is xd upon capital D, should be integral multiple of lambda, and according to that this x should be equal to, if we equate these two, x should be n lambda capital D upon small d, where n are integers, so 0 1 2 and so on. Now by using this expression we can find the position of various bright fringe. For central fringe, if we are talking about the central bright fringe, we have to put n is equal to 0 and we get x is equal to, for bright fringe n is equal to 0 and we get x is equal to 0, and we assume it as x naught so that it represent that it is for n is equal to 0. Again for first bright it is n is equal to 1, and for that x1 will be d lambda over small d. Similarly for second bright n is equal to 2 and x2 will be 2d lambda over small d, and so on. So for general, for nth bright fringe we get xn is equal to n d lambda over d, and if we want to find the fringe width then we have to take the difference that we will do later. So this is the position, this xn represent the position of bright fringes: central bright fringe, first bright fringe, second bright fringe, similarly third, fourth and up to nth bright fringe. Now for destructive case, in case of destructive interference, the path difference, which is xd upon capital D, it should be equal to odd multiple of lambda. It should be odd multiple of lambda by 2, that means 2n minus 1 lambda by 2, and if we solve this or equate this we get x is equal to 2n minus 1 d lambda upon 2d. So this is the value of x, or the position for that dark fringe for the destructive interference. Now here in this case n will vary from 1 2 3 and so on. for 0 it will be -1, this term will be -1, which is contradictory, which is not valid, so it will start from n is equal to 1 and so on. So first dark fringe we get at n is equal to 1, and for that x1 should be d lambda over 2d. For first dark fringe it is d lambda over 2d. For second dark fringe n should be 2, and the answer we get for second dark fringe n is equal to 2, that means x2 is equal to this is 2 to the 4 minus 1, that is 3, so it will be 3d lambda over 2d and so on up to nth fringe. For nth dark fringe xn will be minus 1 d lambda by 2. Now this is the position of dark and the bright fringes that we are getting on the screen. For fringe width we have to find the difference of nth and n minus 1th fringe position. To find the fringe width we have to take the difference of these positions at n and n minus 1. So we'll find for both constructive and destructive case. For constructive case this xn is equal to nd lambda over d. So beta fringe width is denoted by beta, and it will be xn हो जाएगा n d lambda over small d minus n minus 1 d lambda over small d, and if we solve this we get d lambda n d lambda over d minus n d lambda over d, which will cancel out, and this minus and minus plus, so we get beta is equal to d lambda over small d. This is the fringe width for constructive interference. In case of destructive, beta dash, we are representing it now, beta dash for destructive, it is equal to, for nth term it is 2n minus 1 d lambda over 2d minus, for n minus 1 it is 2n minus 1 minus 1 d lambda over 2d. On solving this again we get the value d lambda over small d, that is beta dash. So this is the fringe width for destructive interference. Now we can observe that both the values are same, that means whether the fringe is bright or whether the fringe is dark, in both case the fringe width is same. That means the fringe width for constructive as well as for destructive interference is same and is equal to d lambda over d. Now it depends on d, lambda and small d. That means if we change any of the component in the setup, the value of the fringe width or the width of the fringes that we are getting will vary. It depends on d, lambda and small d. This is the fringe width of interference fringes that we are getting on the screen, and we can define it as the separation between two successive bright or dark, either we have to take bright or we have to take dark fringes. We can't take alternate fringes because it will be bright and dark. That will not help us to find the separation, the fringe width. So for fringe width we have to take the separation between two successive bright or two successive dark fringes. If we plot the curve or the intensity distribution graph for that, during interference, this type of intensity distribution curve, this curve is known as intensity distribution curve, can be obtained. Now this curve shows minimum and maximum intensity. By the formula of intensity we know that its maximum value is when cos phi is equal to plus 1 and its value is I is equal to k a plus a ka whole square, that means 4k a square, which is a constant. Similarly, this is the maximum value, and similarly its minimum value is k a minus a ka whole square, that means 0. So here all the points with 0 value of intensity show minimum intensity or show the dark fringe, while the peaks we are getting, these peaks are of constant amplitude and its value is 4k a square, right? The maximum intensity we are getting is 4k a square corresponding to these peaks, and it denotes bright fringes. So the central fringe is called central bright fringe, which we get at n is equal to 0. N is equal to 0 is for central bright fringe, and further values of n will give us first bright, second bright, similarly first bright, second bright, and alternately we get dark fringes. So we get central bright, then first dark, then first bright, then second dark, then second bright, then third dark, and so on, and symmetrically on the other side of the axis. These are the values or the positions that we have just find the value of x. These are the positions at which we get these fringes, means on x axis or on horizontal axis we have represented x, which is the distance of fringe from the center O. So this value represents the distance of fringe from the center O, and this curve is called intensity distribution curve, and it shows that the maximum intensity is constant, means if there is a bright fringe, it will all bright fringes are of same maximum intensity. This is shown by this curve and by this formula for Imax is equal to 4ka square. Now to get such type of interference that you can observe clearly, so such type of interference is called as sustained interference. Sustained interference means the interference that you can observe clearly, or the interference pattern in which the positions of maximum and minimum intensity on the screen are not changing with time. Means sustained interference means such type of interference pattern have fixed position of maxima and minima with respect to time. Means with time the position of bright and dark fringes is not changing, then such type of interference is called sustained interference. Now there are certain conditions to obtain sustained interference. Like first condition is the two sources that we are using, they should have same frequency and wavelength. So the sources that we are using that are emitting the waves, those are superposing, that sources should emit the waves of same frequency and wavelength. Second is they should be coherent, the sources should be coherent, or the waves coming from those sources should be coherent. Next is for better contrast, the amplitude of the interfering waves should be equal. We have to put the amplitudes, means A1 should be equal to A2. So the amplitude of the two waves that are coming for interference should be equal. Next thing is the sources should be narrow, or the slits that we are using, that should be narrow. So sources should be narrow to get better sustained interference. Next condition is these interfering waves must travel along the same direction, or if they are not exactly in the same direction, then at least nearly along the same direction. So these waves should travel nearly along same direction, right? Next thing is these should be monochromatic. The waves that we are using should be monochromatic and are in the same state of polarization. This is the next condition, that the waves we are using are in same state of polarization. And to have sufficient fringe width, the distance between the two coherent sources should be small, and the distance between the sources and the screen should be large. Since we know the formula is d lambda over small d, so from that relation we conclude that the distance between the two sources, that is a small d, it should be small, and the distance between the two sources and the screen, that is capital D, should be large, so as to get the sufficient fringe width or large value of fringe width, or to observe interference clearly. This should be the condition. So to get sustained interference, these are certain conditions that we have to keep in mind. Only then we can get sustained interference during the experiment. Since we define interference as the redistribution of energy, so there is no increase, no addition or subtraction of energy, or I should say there is no creation or destruction of energy. The energy for the whole system, whole setup remains same, it just redistributed at different locations in different amount. So initially the amount was different for different points. Later on, after the interference, that amount of energy redistributed for different points. So overall, the law of conservation of energy is valid in case of interference. Interference pattern or interference is the phenomena which follow the conservation of energy. It doesn't violate the law of energy. There is no creation or no destruction of energy. It is just the redistribution of energy at different locations of that screen. So that's all. In next part, that will be the third part, we will be comparing the intensities for maximum and minima, or for bright and the dark fringe, as well as we will study about the interference pattern with white light. If the source is white light, what will happen to that interference pattern, that we will also discuss in the next part. For that, stay tuned. Thank you.